Now we'll take a very simple example of how the Ford-Fulkerson algorithm, when applied to a problem, to a flow network for finding the maximum flow and also the minimum cut. So the example that we take is from the textbook Introduction to Algorithms by Corman, Lizerson, Rivestenstein. So first we make the flow network. And then we apply the Ford-Fulkerson algorithm. So we have source node S and we have vertices V1, V2, V3, V4 and T. We have edges S2 V1, S2 V2, V2 to V1, V1 to V3, then V3 to V2, V2 to V4, V4 to V3, V3 to T, and V4 to T. The capacities are 16, 13. So S to V1 capacity is 16, S to V2 is 13, V2 to V1 is 4. Then V1 to V3 is 12. V3 to V2 is 9. V2 V4 is 14. V4 V3 is 7. V3 to T is 20. Then V4 to T is 4. So this is our graph. Call it G. So initially we take the flow as 0 and make our residual graph GF. So step 1 is we find an ST path. So initially we have a flow equal to 0 and we find the ST path. So first we make the residual graph when there is the flow is 0. So we start with again the same. So we find ST path, we can take S, V1, V3, T and we have to augment. But before we make our GF when there is 0 flow. So for GF, since all flows are 0, capacity conditions are satisfied and also conservation conditions are also satisfied. So if we remember the rule to make GF when flow is 0, so how much flow we can increase? So because it is 0, the flow we can increase is the amount of the capacity itself, and there is no backwardness since there is no flow. So initial GF for F equal to 0 will be identical. So just to save my space, this is also GF for the starting case when F is 0, the flow function is identically 0. So this is also the GF for the initial graph. So next step is we find ST simple path and then augment. We perform the augment operation. So ST path, we can find several paths. We can take for example S to V1 to V3 to T. This is a simple path. After finding a simple path, we find the bottleneck. So bottleneck is the minimum residual capacity. So these are called residual capacities of the residual graph. Minimum residual capacity along any edge. So we have 16, 12, 20. This is the bottleneck. Bottleneck is 12. So we have found the bottleneck 12, and the path that we follow is this. So we perform the augment operation. So in augment operation, what we do is along forward edge, so all are forward edges. Along the forward edge, we increase the flow by the bottleneck, which is 12, and along the backward edge, we decrease the flow. Since there is no flow, flow is 0 initially, so we increase the flow to 12 along this path. Remaining flow is 0 already. So we make the flow. So just flow values will show using the circles. So this actually becomes the flow. I will rewrite the capacity 12. So flows are 12 along this path like this. So this is new flow. Rest where I have not drawn the circles, it is assumed that the flow is 0. So for this new flow, we once again modify the residual graph. So again, to save space, you can view this again as G, because now G is identical with GF. So just to save space, I am not redrawing it. So just see here, we have capacities and flow are there. Now with respect to this this flow, so flow has changed. This initial flow, call it F0. Now this is the flow is F1. So flow F1 is shown on G. So I will use this for showing the flow, the graph G. So we make GF1 for this flow F1. So once again we have to draw the residual graph, call it GF1. We make with the same set of vertices but with different edges. So we make S, V1, V2, V3, V4 and T. Now the edges are. So whenever there is flow is 0, we get only forward edges. So all these edges are identical. Only change is along this path. So we make identical of weights 13, 4. So just make it forward at 13. So 4. Then we have 2 to 4 is 14. 14. These are residual capacities. 3 to 2 is 9. 3 to 2 is 9. Then 4 to 3 is 7. 4 to 3 is 7. 4 to T is 4. Now we have to consider this. So S to V1, how much we can increase? It will be residual capacity of the forward edge, and how much we can decrease for backward. So both will have forward with weight 16 minus 12 equal to 4, backward with weight 12. So we draw both forward and backward. 4 and 12. Now V1 to V3. For forward, no forward edge because capacity is full, only backward edge of weight 12. Then 3 to T, forward the difference 8, backward 12, 8 and 12. So this is our GF1 for flow F1. So here also we do the same thing. First find an ST path, ST simple path, then augment the path. So now we can find another path like S, V2, V4, T. So here the bottleneck is 13, 14, 4. 4 is the bottleneck. This is the bottleneck along this path. This is the path. This is the bottleneck. So we perform the augment operation. Here we consider our flow. So forward edges, all are forward edges, we should increase by the bottleneck, which is 4. So not shown values are 0 flow. So we add the flow, add 4. So we write here 4, 4 and here also 4. So this is our new flow. Change it to F2. New flow F2. Now we have to make residual graph for this F2. So here these here we can see. So now the only affected edges are along this path, rest is same. So if we consider this, these edges are same, only change is here. Now we make GF2 once again with same set of vertices, S, V1, V2, V3, V4 and T. This set of weights and edges are same. So between S and Vn, 4 and 12. 4 and 12. 4 and 12. 1 to 3. 1 to 3 we have 12 backward edge with 12. 12. Then 3 to T we have forward 8, 8 and backward 12. 8 backward is 12. Then 2 to 1 is 4. 2 to 1 is 4. Then 3 to 2 is 9. 3 to 2 is 9. 4 to 3 is 7. 4 to 3 is 7. This we have to see. Yes. So here the difference is 9. So forward edge having weight 9, backward edge with 4, 9 and 4. 9 and 4. 9 and 4. 2 to 4 we consider. Forward the difference 14 minus 4 is 10. Backward 4, 10 and 4. 10 and 4. Then 4 to T, V4 to T, no forward edge because flow is full. So only backward edge of weight 4. So this is the residual graph. Once again we have to find ST path, simple ST path. So we try, we go from S to V2. Then what are the options? We can either go V1, V3, VT, or we can go to V2, V4, V3, T. There are two paths. You can choose any one. Let's take this S2 V2 V1 V no, this is backward edge. So we have this path S2 V2 V4 V3 T. So we find the bottleneck. Weights are 9 10 7 8. So 7 is the bottleneck. This is the bottleneck. So we make the path S2 V2, then V4 V3 and finally VT. So we augment by bottleneck, which is 7. So forward edges we add by flow 7, backward edges decrease the flow by 7. So here once again we consider forward edge. This is forward edge, so increase the flow by 7. Increase the flow by 7. So this will change to 7. New flow, no, 4 plus 7 is 11. 11 it becomes. Next we have V2 to V4. V2 to V4. 2 to 4. This is forward edge. Again, add 7, so we get 11. New flow is 11. Then from V4 we move to V3. 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 So flow is 0, so it becomes 7. Then last we have 3 to T. 3 to T. We have forward edge, so increase the flow by 7. Current flow is 12, so 12 plus 7 is 19. So this becomes, new flow is 19. Now call this new flow F3. Label it F3. Now we have to make the residual graph GF3. So here everything is same except for the path. So again we redraw, call it GF3. GF3 we make same set of vertices S, V1, V2, V3, V4 and T. So except for the path everything is identical, change is only along these edges. So we copy first 4 and 12, 4 and 12, then 12, 3 to 1 is 12, 3 to 1 is 12, 2 to 1 is 4, 2 to 1 is 4, and then we have 2, and this will change. This will change. 3 to 2 is 9. 3 to 2 is 9. This will change, this will change, this will change, then we have this T to 4 is 4, T to 4 is 4. Now along the path 1, 2, 3, 4, this will change, 1, 2, 3, 4, and we also this will change. So now we consider these values. We have to just see this original flow F3 along this path. So first S2 V2 we consider. 13 minus 11 is 2. 2 we can, forward is 2, backward is 11. 2 and 11. 2 and 11. Next we have 2 to 4. 2 to 4. 14 minus 11 is 3. Forward is 3, backward is 11. 3 and 11. 3 and 11. 4 to 3. 4 to 3 is only backward. Capacity is full. Backward 7. 7. Now 3 to T. The difference is 20 minus 19 is 1. Forward is 1, backward is 19. 1 and 19. 1, 19. So once again we find simple S to T path and then augment. So start with F, we can have only two possibilities. If we move to V1, the only outgoing edge, it makes a cycle, so this is not possible. The only possibility is we are forced to move to V2. This is the only choice. Now from V2, so we can mark this. This is the only option we have. From V2, we have two possibilities, either move to V1 or move to V4. If you move to V1, then again the same problem, it creates a cycle. So this possibility is ruled out. So now the only possibility is we have to move to V4. So just mark it V4. Now what happens at V4? The only outgoing edge, it makes a loop, so not possible. So we have found that there is no simple ST path. So we conclude that. So here the Fulkerson algorithm stops and we can find the value of the flow. So value of the flow F3 is flow out of S. We compute flow out of S. Flow out of S. So flow out of S is 12 plus 11 is 23. 12 plus 11 is 23. Now we can also find the minimum cut. So for finding minimum cut, we start with S and consider what all vertices we can reach starting from S. So from S we can reach V1, V2, V1, V2, V4. V4 we come back to V2. So S, V1, V2, V4. We cannot reach V3 and T. So A, S, V1, V2, V4. V1, V2, V4 and B is the remaining vertices V3 and T. V3 and T. So now we compute the capacity of the cut AB is simply capacity out of A. Capacity out of A. So we mark the boundary S, V1, V2, V4 like this. S, this we have marked our boundary. Now capacity out of A. So we consider edges which are going out from the set A. So this is our set A, remaining is our set B. So we mark the edges. So first we find this V4 to T. Capacity is 4. So this I will mark. So here we can compute CAB is 4 plus Next we have this V4 to V3, 7 plus 7 plus, and one more. So this edge is coming in, we should not count it. Just look around the boundary. This edge is going out and capacity is 12. This plus 12. Any more? We do not have any other edges. So just compute it. Once again we get 23. So this is also equal to value of the flow, F3 final flow. So max flow is equal to min cut, and using the Fulkerson algorithm we can find both maximum flow as well as the minimum cut.